Okay, presumably we're recording. I'm doing one question from a January 2022 paper for Unit 4, Further Mechanics, Fields and Particles. So this is the exam my students will be taking in January of 2025, and I just wanted to go through one question from the paper, and that's a question on capacitance. So we've just done the core practical, and this is question 14 from the exam, and I'm going to go through it with my answers. Okay, so to start with, when you're doing these questions, you need to make sure you understand the core practical. So the core practical to do with charging and discharging a capacitor is core practical 11. So you need to know how to charge and discharge a capacitor. So in this question, so I gave it to them just after they'd managed to do the charging and discharging a capacitor, and they timed it and they've plotted their graph and they've written their report for me. So this is for the international A level. So it says a student built the circuit shown. So you have a resistor, 5 volt DC supply, 2 ammeters in the circuit, which you'll find out why in a moment, in a series with a capacitor, and it's got a switch on it. The capacitor was initially uncharged, so there's no charge. So it will start charging when you close the switch. So she closed the switch and plotted a graph of current on ammeter A1 against time. So you got the current in milliamps, so be careful that you know that's in milliamps, and against seconds. So it took about 30 seconds to completely charge up. Now, if you remember, the charging and the discharging circuit current graph is always decreasing, because at the beginning the charge flow is fast, and as time goes on, when it's discharging or it's charging, in this case, when it will be more difficult to push the current through as the capacitors become charged. So if this is the positive of the cell, this is the negative, then this side will be the positively charged side of the capacitor, and this side will be the negatively charged side of the capacitor. And when it's fully charged, it will reach the same potential as the power supply that you're using, in this case 5 volts. So when it's fully charged, at 30 seconds, it will reach 5 volts. So this is the graph of current on the ammeter against time. The question is, why have they put 2 ammeters? Well, you'll see in a moment is one of the questions. So it says, determine whether the initial value of current, which is here, the initial value of current, so the maximum current is at the beginning, so it's the maximum flow of charge onto the plates, on the graph is consistent with the value stated on the circuit diagram. Well, the value stated on the circuit diagram is 5.0 volts and 33 kilo ohms, which is 33 times 10 to the 3 ohms. So don't get confused. There's a kilo there and then there's a milli there. Okay, so consistent with the value stated in the graph, so R is 33 times 10 to the 3 ohms, 33 kilo ohms. Voltage is 5.0 volts. You'll notice both figures are given to 2 significant figures. Okay, so then you want to work out the current from these values. So I'll just move the paper up for you so you can see my calculation. So I would be V over R, so it's 5 divided by 33,000 ohms. That gives 1.5 times 10 to the minus 4 amps, which is 0.15 amps. Okay, so you then say, well, this is consistent with the value shown on the graph, because the value shown on the graph is here, 0.1, halfway between 0.1 and 0.2, so it's the same as the value shown in the graph. So you can see the calculation backs up what the current should be at the maximum rate. Okay, that's the only time you're going to get the maximum current. After that, as the charge on the capacitor builds up, it will actually be more difficult to push more charge onto the plates, okay, because there will be some resistance from the charge that's already there. Okay, because remember, the negative charge is electrons will be filling up on this side. So if it's already full of electrons, it's difficult to put more electrons onto that plate, and likewise pull more electrons off that plate. Okay, so then it says explain how the current on ammeter 2, so that's the second ammeter after the capacitor, if you like, in direction of conventional current. So if you think of conventional current flowing this way, it keeps flowing until 30 seconds when the current reaches 0. So it will keep on flowing through this series circuit. Well, it's a series circuit. Now you should know from GCSE that the current anywhere on a series circuit should be the same. So how do you answer this? In a series circuit, I've written, the current is the same everywhere. So that's 1 mark for this. Yeah, 1 mark for that. So A2, the second ammeter, will vary in exactly the same way as the current that you've detected and measured on ammeter 1. So there's no difference between them. So that's a little bit of a trick question if you haven't thought about it. So that's part B. Part C has mark schemes available if you want to look it up. I haven't got the mark scheme here to show you on the camera, but part C then says determine the capacitance of the capacitor. Well, this was a task that you could do from Core Practical 11, would be to determine the capacitance of an unknown capacitor, for example. So what I'm saying is, to do that, you need to find the time constant from the graph. That's the easiest way. And that's the time taken, or the time it takes. So let's just change the English there. Time it takes to fall to 36.8% of the initial current, and that's 1 over E, yes, where E is the value, which is 2.718. Okay, you can find it on your calculator. It has it's a constant in maths. Okay, so whenever it falls to 36.8% of its initial current, we call that the time constant. So you can look at the graph and see, well, it starts at 0.15. So what is 37% roughly of 0.15? Yes, so remember over here we've agreed the starting current is 0.15 milliamps, I should write. Okay, so if you know the starting current, you should be able to work out what's 37% of that, and you'll see in my calculation the time constant, the 37%, 0.37, so I've just rounded up because 2 significant figures is sufficient for the purpose of this question, because everything has been given to 2 significant figures. So that comes to about 0.055 milliamps. Okay, that will be the current at that value. When the current's at that value, that's the time constant. So if you look at the graph again, 0.055, 0.05 will be here, yeah, and 0.06 will be there. So it's halfway between these two. You go there and you see it's roughly 7 seconds. Okay, so you go 0.55, the closest is 7 seconds, and that's accurate enough to get the marks for this question. So 7.0 seconds, yeah, or thereabouts. Once you know the time constant, then the time constant is the time at when the current is equal to the value we just calculated, which is 37% of the maximum current. So that will give you time constant of 7.0 seconds, and you know this equation, time constant is equal to resistance of the circuit times the capacitance of the circuit. Now we know the resistance of the circuit was 33,000 ohms, and we know now 7 seconds, so you just got to do some algebra. The capacitance is a time constant divided by the resistance. So 7.0 divided by 33,000, and you'll get approximately 2 significant figures, 2.1 times 10 to the minus 4 farads. So that's how you get 3 marks, 1 for working out what's 37%, 1 for working out the time and putting it into the time constant equation. Now all these equations are given to you, yeah, on the capacitance part of the data at the back of the paper. So here's capacitance, yeah, and over the page, let's see if they've actually given you the time constant formula. No, there's not a time constant formula, but RC is the time constant. So they haven't actually told you that time constant is resistance times capacitance, but my students have been told that, and that was a focus. So this is how they did this on their own graph. So I've only done it this method, but you can use the graph with any of the equations that are given. For example, the discharge circuit, because it's the same rate of the decrease of current against current 0 against e to the minus t over RC, if you can read that. So you can also get values like I did. You can just get values from the graph at different times, and then the only unknown will be the capacitance. So you can do that, but that's a more long-winded way of doing it, but that will also get you all the marks. So once you've seen my method, see if you can use this equation for current. For charging, it's exactly the same equation as the discharge equation. So you could use this equation and plug the values in from two values from the graphs. You take an I value, you know the maximum value, you know E, and you put the time in. It doesn't have to be the 37% value of time. You can put any time value in corresponding to the current. So that time value from the graph will be the corresponding current that is at that time, and then the only thing you don't know is the capacitance. Okay, so that might need a bit of zooming in if you can't see it clearly, but have a look at a Unit 4 list of equations. Okay, so that's how you get the capacitance, and you only need to give it two significant figures. So you can either put 2.1 times 10 to the minus 4 farads, or you can say that's 210 microfarads. When capacitors are often given in microfarads. So part D of this question then wants you to determine the charge stored on the capacitor after 30 seconds. So why are they saying after 30 seconds? Because after 30 seconds we know it's fully charged, so we know the voltage is 5.0 volts. And going back to the equations for capacitance, you should know the equations for capacitance if you've done the capacitance chapters, and capacitance is basically the charge to voltage ratio. So how much charge does it store per unit volts? Okay, well, we know that's 5, and we know the capacitance is just calculated here, and you can put the values in. Once you do that, you'll get 5 times 2.1, which should give you 10.5 times 10 to the minus 4 coulombs, to 3 significant figures. And again, you should really round it up to 2 significant figures, and 10.5 will become 1.1 times 10 to the minus 3 coulombs, or 1.1 millicoulombs. Okay, that's the charge stored when it's fully charged. It's actually the charge stored on each plate of the capacitor. Okay, because the total charge stored in the capacitor is actually 0 if you think about it, because the positive plate will have this in the positive sense, and the negative plate will have this much charge in the negative sense. So actually the total charge is 0. So think about that. It's a key point. So capacitors actually separate charges into positive and negative. Each plate becomes one and the other. Okay. Determine the part E is then determine the maximum energy stored by the capacitor at obviously the same voltage. So the maximum energy is when it's at 5.0 volts. Okay, so when it's fully charged. And energy from the equations is half QV. There are alternative equations for energy stored in the capacitor. Half QV, and they put for energy, they put W for work. So half QV, half CV squared, or half Q squared over C. So you need to be able to use all these three forms. Well, the simplest one is this one, because we just use the charge, and we know the voltage is 5, so there's no squaring required if you use this one. Okay. Once you do that, looks like my camera's gone a little bit out of focus. Sometimes does that in dim lighting. Okay, but I think you can just about read it as we come to the end of the question. This is an 11-mark question, which I gave them as a mini assessment after they had just finished their core practical 11. So energy stored is half QV. Q we just calculated, but I would use the more accurate 3 significant figure value, 1.05 times 10 to the minus 3, because I'm using the decimal place here. Multiply by 5.0, you get about 2.6 times 10 to the minus 3 joules. I'm sorry about the focus going. It is quite annoying when this camera loses focus. Okay, and that is the end of the 11 marks. So 2 marks there. and here likewise putting the numbers in, one for getting the answers. They'll probably give you a mark for 3 significance figures or 2. And that's the end of this question. So I'm going to upload that to YouTube. So please like the video if you found it useful. Share it with your friends if they're doing the same exam, and I'll be doing more of these mini videos in the build up to the end of the course. So mainly focusing on Unit 4, and for Year 12 we'll be doing some Unit 1 questions as well. Okay? If you want to know when the next video is ready, please make sure you're subscribed and you'll be notified. Thanks for watching. Bye for now.